you make a counter that has some sort of specific, something that does something a little different. And so he has in his directions that in these problems we're referring to counter C, which is a 4-bit counter with parallel load, and that it's a synchronous positive edge trigger device, and the load input is also synchronous. That means it does its thing on the positive edge of the clock. So every positive edge of the clock, if it's enabled, then if its load equals 1, then it loads a new value. Otherwise, it counts. So let me tell you what that means by counting. So it has these 4 outputs, Q0, Q1, Q2, and Q3. And on a load, it's going to load whatever values are on these D inputs right here. So let's say I had zeros right here, and I had a 1 on load. So that means, and enable is 1. If enable is not 1, then nothing happens. But or if enable is not 1, then whatever was on Q before stays there. That value just stays. So if 1 is on load, then whatever is on these wires right here, D0 to D3, those get loaded over here. And the way I wrote these is backwards for how we would think of them. So let me change it to our order. Okay, so Q0 is going to represent the least significant bit. And so we just loaded 0, 0, 0. And now let's assume that 0 is load from here on out in this discussion. And we're going to see what happens as the clock, when the clock goes to the next positive edge. So on the next positive edge, these values of Q are going to change. Q3, Q2, and Q1 will stay the same. Q0 goes to 1. And then on the next value, Q1 changes to 1 and Q0 changes to 0. And then on the next clock cycle, Q1 stays the same, but Q0 toggles. And then on the next clock cycle, what happens, the way the counter works is every time the rightmost bits are all 1, the next bit, in this case bits 1 and 0 are 1, when those are 1, on the next clock cycle, the next highest bit, which is Q2, it's going to toggle to 1. And these rightmost bits are going to turn 0. The last bit toggles on every clock cycle. So right now it's 0. On the next clock cycle, it's going to be 1. Now, if you look from the point of view of bit 1 right here, when bit 1 looks to the right, it sees all 1s. There's only 1 bit there, but it's a 1. When the bits all to the right of a given bit are all 1s, that's its signal to change, and then the ones to the right will stay 0. So this bit right here, all the bits to the right are 1, so on the next clock cycle, it's going to change, and those 1s will turn to 0s. Okay, now, on this clock cycle, there's no bit that's going to look to the right and see every bit to the right as being 1. So none of these other bits are going to toggle, but the last bit toggles on every clock cycle. So the next one we get would be 0, 1, 1, 1. Now, based on what I was saying before, if you are this bit right here, when you look to the right, you see that all of those bits are 1. That's your signal, time for you to toggle. And all of these ones will turn to zeros. Now, on the next clock cycle, nobody can look to the right and see all ones, so the only thing that will happen is this last bit will toggle. And now, for the second bit, when it looks to the right, it sees all ones, so it will toggle, and that 1 will turn to a 0. Now, on the next one, nobody sees all ones to the right, so the only thing that happens is that last bit toggles. And now on the next clock cycle, this bit sees all ones to the right, so it turns to a 1, and these turn to zeros. And that is the pattern, and with that pattern, you end up getting the binary numbers from 0 to 15. And then on the next clock cycle, everything are ones, and so they all go to zeros. They all go back to zeros. Okay, so that is how it actually works. But if you look at these values, the values of these, the value is 0, this is 1, this is 2, this is 3. Do y'all know how to turn these numbers into decimal numbers? Yeah, okay. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And so using that, so it would be, it's basically AND gates. I think it's AND gates, but it's looking to see if everything to the right, if everything, all the bits smaller than it are ones. When all the bits smaller than it are ones, then it changes. So that is how the counter works. But you can assume that it works correctly for these problems. So you're not actually changing the designer of the counter. You do have to know how it works, but the design of the counter, but you're not actually going to change it. So for this first one, we're determining the clock sequence for this counter. So what we see is that when it loads all zeros. So we will, on these problems, we will assume that the first thing that we get is a load. Okay, so if the first thing that we get is a load, then our first set of numbers that we get is 0, 0, 0, 0, and that corresponds to a 0. And the only thing that we see is going on is that Q3 is our input for load. So we want to pay attention to Q3. As long as Q3 is 0, it's not going to load. So if it's not going to load and we have a 1 here on the enable, then every time the clock has a new clock cycle, it's just going to count up according to how it counts, which is a normal count. So the next clock cycle, it'll go to 1. That's right. Q3, because the load will only work when it has a 1, and that's only going to happen when Q3 is 1. So it's going to just count normally. So we got 0, 1, 2, and the next one would be 3. And then the next one, 4. Oh, and then 5, 6, 7. So 3, 4, 5, 6, 7. and then we get 8. But you see, once we get 8, with 8, Q3 is 1. So Q3 is 1, so on the next clock cycle, it's going to load, and it'll load 0, 0, 0. Because that's what we have here. So the next clock cycle, you'll get 0. And then it'll start counting again, 1, 2, 3, 3, 4, 5, 6, 7, 8, 0. So when you're writing the sequence for the clock cycle, you only have to write to where you get to the first repeat. 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, dot, dot, dot. Okay, so any questions on that? I did want to do the QR code. Thank you. I'm going to stop this recording.